Okay. Good afternoon, everybody. I hope everyone's having a wonderful day. So just a couple of quick reminders before we get started. So on Friday, the take-home test, the second one, will be opening up. It's very much like the same way we did things with the first take-home test. It'll open up. You'll have Friday, Saturday, and Sunday to complete it. There's no time limit on it. It's an open book test. You can use the optional textbooks. You can use lecture notes. You can use the lecture videos. And you're given a series of problems. Take a look at the format announcement if you have not yet already. You'll notice that in this one, you're doing some multiple choice questions, and then you have some written answer questions like on the first test. Are there any quick questions before we proceed? Because I have plenty I want to talk about today. If not, you can always ask me by email or office hours if it's a little more lengthy. But yeah, it'll open up on Friday. Remember, Simon 4's deadline is creeping up, just like I said last day. It is due by the end of Friday. But keep in mind, like I said, I will accept your submission until 8:30 Saturday morning, and there's no penalties. That's just mostly for our purposes, because I'm not going to look at it at 1 in the morning, okay? Just to keep it simple. Okay. So anyways, are we all good to go? Give me 2 thumbs up if we're all good to go. Because I got a pretty interesting lecture for you today. I like to think of all my lectures are interesting, but sometimes I get a little too excited, okay? So this one I can tell you is genuinely going to run deep. And if you walk out of this lecture and you understand everything, you're doing pretty good. Just to be clear. So if the ideas don't click immediately, it's not the end of the world. Just please think about it very carefully. But my goal is to obviously make them click. So hopefully we'll have a good time with this. So I'm going to be exposing a fundamental limit to computation to you today. In particular, I'm going to show you that there's languages that are not recursively enumerable or Turing, or what we call Turing recognizable. That means there is no Turing machine that it can even recognize the language I'm going to present to you. So I'm not even talking about deciding. I'm talking about just recognizing it. So before that, I need to get some setup for you. And this is going to kind of append itself onto what we were talking about today. In particular, it was about, we talked last day about how we can count sizes of sets. And remember, actually, one small remark. I did mention this on the Discord server, but also I did update it in the notes. For some reason, there was a strange typo in the injective definition. Just please take a look at the notes for the quick correction on that. It was near the beginning of lecture. For some reason, I wrote that the Y element was in the other set. It was actually just both X and Y were in A. But I don't know why I wrote that, even though I drew it correctly on the board for you. But hopefully you got the idea regardless. So I apologize for that. It's one of those weird slip-ups that happen every once in a blue moon. Anyways, in that lecture, I talked about the connection between integers and all sorts of different sets. Today, I'm going to be showing you first how you can encode a Turing machine into a binary number. So that's the first thing we're going to do today. And then we're going to see what we can do with that information. So I'm going to first appeal to something I talked about last day. And this is going to be very helpful for us when we talk about listing binary strings. So let's talk about listing binary strings. So you remember last day I talked a little bit about, oh yeah, here's a nice way you can represent each one of the binary strings for, say, a given alphabet. I'm going to use that same idea. I'm just going to enumerate it in a way that's a little easier to see. So listing binary strings. So here's the convention I'm going to pick up. It's a convention to assign integers, in particular positive integers, to all binary strings. All binary strings to have a correspondence. So remember, a correspondence, like I said, is just a pairing of each one of the elements in one set with another set's elements. So here's how it's going to go. This is based on the idea I showed you last day, that little trick I showed you that I thought it was a little easier to see. So if W is a binary string, then we can interpret, one W, so W is the string, it's a binary string, as integer I. So if I give you, say, 1W, here's going to be the idea. As integer I, call W the ith string. So here's the ordering when I talk about this I, what integer I is. So epsilon is going to correspond with 1. Single 0 is going to correspond to 2. 1 is going to correspond with 3. 0, 0 is going to correspond with 4. And so on. So remember, these are my binary strings on one side. These are my positive integers. So you might recall I did this last day, except I'm just not going to care about that leading 1 anymore. Does everybody see that? So notice that when I wrote this over here, remember 1W, that's going to be a binary string that I can interpret as a binary number. And the result of this, when I put the binary string in here, ends up being the number that's on the right. Just like, for example, if I had epsilon, I would have 1 epsilon as a binary string. That's just 1. If I have 1, 0, then as a binary number, interpreting that in decimal, that's 2, right? And so on. So this is how we're going to talk about listing the binary strings. So this is the convention I'm going to pick up. Are there any questions about that? Or is this all good? Because this is similar to what I said last day. So I'm just not going to care about that leading 1 when I write the strings out on this side. So it's okay if there's a leading 0, for example. So what I'm going to do is I'm going to denote the ith string as Wi. That's going to be very important for us. So just please remember that Wi is going to be the ith binary string in this list. So for example, if I look at W1, this is W1. That's W2, W3, W4. Did everybody get it? Just want to make sure we're all good here, because this W notation is going to be very important for us. So it's just going to represent what the string is for the ith number. So if we're all good with that, let me proceed then. So one thing I want to point out, let me just get us moving on over here. My apologies. There we go. My apologies. So today we're going to be considering Turing machines that are encoded with binary. So what you might say, Dan, our definition of a Turing machine, it can have any alphabet, right? Now, what we're going to do is we're going to restrict ourselves just to Turing machines where the input alphabet is binary. That's the only thing we're going to be considering here today. You might ask, Dan, why are we doing that? It's because if you think about it this way, think about the most simplest kind of Turing machine you could have that you can do anything interesting with that's Turing equivalent to our general model. It's actually the Turing machine with a binary input alphabet. So if I can, for example, show you results for the Turing machine with a binary alphabet, then those results would apply for general alphabets. So for simplicity, we're only going to consider Turing machines with binary alphabets. You might ask, Dan, okay, well, like certainly there's languages you can't describe in binary, and that is in fact true. So just be aware that I'm restricting what I can describe with this Turing machine. However, that doesn't really matter because I'm really just trying to show you, hey, look, if this very simple Turing machine that just uses binary has these limitations, and most certainly it's true for any general Turing machine with any alphabet. So restricted to the binary alphabet. So consider Turing machines restricted to the binary alphabet. We will establish results for these so that they may apply to any Turing machine with an arbitrary alphabet. So that's one thing I need to point out to you, is just that we're only going to care about the Turing machine where its symbols are all going to be binary. This is going to be relevant for how we're going to encode the Turing machine. And if you think about it, this isn't really that strange. I mean, we work with computers that encode information with binary, right? I mean, it's nothing too strange. Now, just as a side note, so at the heart of our encoding scheme is the idea of a so-called universal Turing machine, which I'm going to describe more on a high level at this stage. I'll define it more formally in maybe a lecture or two. So you might ask, Dan, what is this? So just here's the idea of the universal Turing machine. So I'm going to abbreviate it as UTM. It is simply a Turing machine that simulates other Turing machines where the input includes the encoding of the Turing machine. So I have a question for you. If I think about a Turing machine like an algorithm, then what would I think of the universal Turing machine? A Turing machine that simulates other Turing machines. Does anybody have any ideas of what maybe a good analogy for what the universal Turing machine might be? Well, we can go even further than that. We can go even further than that, believe it or not. See, yes. So you said the key thing is that it's like a program. So you could think of the Turing machine like a program that I read to this Turing machine. So what is the universal Turing machine then? Yeah, it's a machine that can have any input. But it actually will do something quite specific for us. It simulates the Turing machines for us. So think about it. If that's an algorithm, and it runs any algorithm that's fed to it, and it means it's programmable, right? But what is that? What do we call that? Just starts with a C. What is that? It can be C++, that is true, but I'm thinking of something even bigger than that. Well, I'm thinking of a computer, a stored program computer. So you could think of this universal Turing machine like a stored program computer. And anything that's equivalent to this, which does include things like C++, is what we often call Turing computable. But I'm going to talk more about those details at another time. So I'll say you can view, but like I said, it is very much like a meta algorithm, right? That's exactly the right idea. But you can view the universal Turing machine like a stored program computer, which is a fundamental aspect of all computers, is that they store the program on itself, right? So the whole idea here is that this is a Turing machine that's given an encoding of a Turing machine, and it simulates it. So when I mean simulates, I literally mean like it will, so you can view this thing like a computer that's being fed a computer program, and it executes it. So that's fundamentally the idea that's interesting about the universal Turing machine, despite the fact it's literally just a Turing machine. It's kind of interesting in its own right. So I'm just going to say the universal Turing machine is called universal. It's called universal because it can take the description of any Turing machine and carry out its execution. So what I mean by that is that, say, for example, you give it a Turing machine and it never actually halts. Then the universal Turing machine will not halt either. It goes into an infinite loop. So if it halts, the universal Turing machine halts. Do you get the general gist of this idea? But universal means, in the most broadest sense, yeah, it can take any Turing machine and it can execute it. And there's a lot of equivalent different ways you can talk about what a universal Turing machine is in the same universal sense, with all sorts of different computational models or approaches. Some people would say, oh yeah, programming languages, they could do these kind of things too. They can describe languages and, they can describe programs, and you can indeed run them within the context of compiling a stored program that executes on your computer. Like, there's all sorts of different things you can go with this, but I'm just going to keep this high level at this stage. I'll talk more about this later. Maybe not today, but another day. But I just want you to be aware of this fact. What we're going to be concerned with is, that says we will be concerned with, that's an R there, concerned with is encoding the Turing machine. Which, this would be what you'd give to the universal Turing machine. But we only care about the encoding of the Turing machine. The universal Turing machine also can take input. So it takes the input string W, encoded in binary, that would also go with this Turing machine encoding. That's how the universal Turing machine takes its input in. But we're only going to be caring about how we encode the Turing machine that gets fed to this universal Turing machine as input, okay? Is that clear, everybody? So we're only going to care about the encoding of a Turing machine that can be given to the universal Turing machine. But we're going to use that theory to help us prove a property today, okay? So I'm going to first start off by describing how I'm going to transform my Turing machine description into a binary string. And then once we are from there, we're going to see if we can identify a language that is not recursively enumerable. Does the game plan sound good with everybody? Okay, so let's proceed. So let's talk about how we're going to encode our Turing machine. Now, I must stress this isn't the only way you can encode a Turing machine, but this is most certainly a common way. I don't make any claims of efficiency or anything like that. I just care that it computes it. Okay. So let's talk about encoding a Turing machine. So we got to first talk about the states. So I'm first going to talk about the states. Now, I'm going to assume that the states, transitions, and directions are all going to be prescribed as I do in this convention. There's actually a very usefulness to the way I'm going to write this out. So you might ask, Dan, where's Q0? You'll see very quickly that the way I'm going to adopt the names of the states actually corresponds to how the binary string is going to get encoded. So it's a feature of the encoding scheme. So I'm going to assume Q1, Q2, all the way up to QR for some R are the states. Okay, so here's the great part. Okay, Q1, this is going to be what we're going to call the start state. We're going to have only one final state here. Now, believe it or not, you can take any Turing machine and you can make it so it has only one final state. I'll let you think about that. It's a very interesting question. But I'm going to ensure that Q2 is always going to be this final state when I do this. And then all of the other ones are just going to be your other states. Is that clear, everybody? So there's going to be Q1 through QR. Q1 is going to be designated the start state. Q2 is the final state. And all the other states are numbered Q3 all the way up to QR, where R is the number of states. Okay, tape symbols. Let's talk about the tape symbols. So we're going to have Q1, not Q1, we'll have X1, X2, all the way up to XS for some integer S. So you might ask, Dan, what are the symbols going to be for our tape? Remember, this is binary, so I'm going to assume. So this is how I'm going to go about it. So X1 is going to be 0. In fact, I'm going to list one more here. I'll have X3 here, because I'm going to need that one. X1 is going to be 0, X2 is going to be 1, and X3 is going to be the blank. And then you can use X4, X5, all the way up to XS. These could all be your other tape symbols as you need them. So far, we're doing okay. So these are just names I'm giving the states and the tape symbols, and they're going to correspond to the symbols that or special meanings that I'm giving them. Why? Because we need that for an encoding scheme. So everybody agrees on the rules of how we're going to represent this binary string. So that's the tape symbols. How about the directions? So let's talk about the directions. Remember, we just have left and right. So I'm going to call left is going to be what I call D1. And R is what I'm going to call D2. Like I said, there's many ways you can encode a Turing machine. This is just going to be one of them. So I got to describe to you how you give a transition, right? Because those are very important for how we encode the Turing machine. to encode delta if we are given delta of qi xj is equal to qk xl dm. Like I said, there's a lot of symbols in here, and I must stress that I, j, k, l, and m are all positive integers. Like I said, you didn't expect to see this many variables all at once, but that's what we're doing today. So here's how we're going to encode the string. If we're given this, then encode it as 0 to the I, 0 to the I, 1 0 to the j, 1 0 to the k, 1 0 to the L, 1 0 to the M. So these ones are going to operate like our separators. Like, remember when I was talking about unary earlier? And I said, oh yeah, we have to have a separator or some delimiter. That's what these ones are going to represent for us. So they're going to separate these zeros out. And the number of zeros for each one of these is going to tell me the state, the tape symbol, what state it needs to go to, what I should write to the tape symbol, and the direction. That's what each one of these numbers that I, j, k, l, and m correspond to. That's why we actually named them 1 through r, 1 through s, and 1 and 2. Is they're going to be telling us how many zeros we're going to write down here in the binary string. Does everybody understand that? So this shouldn't look too strange to you if you think about it that way. So this is the convention I've just selected here for us. I'm not saying this is the only way. This is just one way. We just need some way of encoding the Turing machine into binary. So this is how you can do one transition. Let's do an example. I have 2 examples in the notes. I'll do one here. So for example, if I give you delta q1 1 is equal to q3 0 with right. The way I can write this out, so remember q1 with a 1, then it transitions, sorry, the move is to go to q3, it writes a 0, then it goes right. So look at the format I have here. Identify what I, j, k, and l, and m are. So q1 is just going to be how many zeros? 1 0. So I have my separator. So this is q1 right here. So that's q1. Sorry, my writing there was a little funny. Then I have a 1. But 1 is encoded as, it says it's x2. But that's what j is, right? So I'm going to have 2 zeros. So this is for my 1. I'm going to have a separator. Then I have 3 zeros because I have q3. So it's the third state listed. So it means I'm going to have 3 zeros. So this is for q3. Then I'm going to have a 1. And now I'm going to write a 0. That's the very first symbol in my tape symbols. So it means I'm going to only write 1 0. So this is for 0. And then, of course, I have my direction. Go to the right. That's D2. But that's what M is. M is 2 here, so I write 2 zeros. Does everybody get the general idea? All you do is you just look at what the numbers are as the indices, or what the symbol just straight up is for your transition. So are we all okay with this? Just don't be shy about asking questions. It's very important. So this describes how you can encode the transitions. So to describe the Turing machine itself, I have to list out all of the transitions. If I accept this scheme, then I know everything I need to know about the Turing machine, believe it or not. So all I need is just some way of listing out all of these. Now, here's the idea. Actually, one other thing before I proceed. One thing I want you to notice is that there's no 2 consecutive ones in this string. That's another feature of why I listed them as I did over here. Is that notice that these always operate like separators, but we want to implicitly use these ones to help us separate certain information. So this would be what I would write for one transition. If I want to write all of the transitions, I'm going to separate each one with 2 ones instead of just one. That sounds a little funny. So let me just write it up here. To encode the Turing machine, it has all the codes for transitions, for all transitions separated by 1, 1. Must stress that's not 11, that's 1, 1. By 2 1s. So here's how you would write it out. So just to be clear, here's how you would write it out. C1, 1, 1, C2, 1, 1, and so on. Cn minus 1, 1, 1, Cn. And each one of these is the code for a transition. So if I give you this string, this actually lists out all the information you're going to need to know to encode the Turing machine. Is everybody okay with this? As a remark, I may mention this fact in the future, but if you ever needed to have more information encoded with the Turing machine, for example, with this universal Turing machine, it's very common you have an input string that goes along with it. I'm going to mention this as a remark. I apologize for this being kind of slathered in the middle of this. So as a remark, if we want to encode more with the Turing machine, example, input W, which is very common, right? Like we have our Turing machine with an input W like in this universal Turing machine. All you do is you append 3 1s like this, then you write W. So you'd have all of this before that. The 3 1s are what we would use to separate each input. So 3 1s operate like a separator for the inputs, but we only care about the Turing machine itself today, okay? So are we all okay with this? So this is just the scheme I've adopted here. So the big thing I really want you just to be aware of is the fact that I've described to you a way I could do this with any Turing machine. Is everybody okay with me saying that? If you need to push back, please push back. So I could take any Turing machine, encode it as a binary string, and each one of these, as I established at the beginning of the lecture, has a correspondence with an integer, right? However, I'm only talking about the valid Turing machines when I say that. In fact, there's a bunch of Turing machines that are going to just be a whole bunch of junk if I were to look at them as integers. So actually, let me write it over there. Let's write it over there. So I got to finish telling you how we get every integer, our positive integers, that correspond to a Turing machine. So the big fact I really want you just to be aware of from what I just stated is that all of the Turing machines that are valid, all of those are countable. Because it is technically a subset of all of the positive integers, because each one of those binary encodings is an integer. Each one is unique. At least one of these is going to represent some Turing machine. So the thing I really want you to notice is that there is a countable number of valid Turing machines. That's the thing that you really need here for us to make the following result work. But I haven't really told you, because remember, the whole big idea is that I want to be able to tell you, okay, so there's some integer I. I want you to have there's going to be some binary string. So I have some integer, a positive integer I, and I want it to correspond to some binary string, which I want it to be a Turing machine, some ith Turing machine. So I want this to fully hold, but there's a problem, right? Some of my encodings of Turing machines don't actually represent, like if I gave you an arbitrary positive integer and I represent it in binary, some of them have leading ones. For example, there's a 1 right at the beginning of the string. That's a problem for us, right? No Turing machine that I've just described over there as a binary string has a 1 at the beginning. So I need some way, some trickery to essentially deal with these so that I have this relationship. So I got to talk a little bit about that. So note, any malformed, these are the unfortunate Turing machines. Sometimes they just don't seem to do anything interesting for us because they just don't have the right number. That is a pun. That is a pun, by the way. It's unfortunate. But we try to do our best for our Turing machines. So any malformed Turing machine, i.e. does not correspond to an integer, does not correspond to an integer, will be considered a Turing machine with one state and no moves. And no moves with no accepting states. So just to be clear, it's just one state. There's no moves that you can make from the initial state, and it doesn't accept. So if I told you that this was the ith Turing machine, and it's one of the malformed ones, what would its language look like? Somebody tell me? What kind of, well, not epsilon. You're very close, though. Empty, exactly. It's the empty language. There is no accepting states, so like I said, we need to have some Turing machine that's going to work for us here, okay? So now, believe it or not, I have this relationship that exists if I take on this as the assumption to do with all the ones that don't correspond to an encoding of one of those over there. So I'm going to define. So first, are there any questions before we proceed? So while you think about that, I'm just going to say, so we can take a Turing machine, interpret it as a binary string, as a binary string which is in turn a binary number. A binary number we have a code. We have a code for the ith Turing machine, the ith TM. This is the Turing machine M with code WI. So this is the WI I was talking about at the beginning of the lecture. So just remember, this is just this is the ith binary string that I described at the beginning of the lecture. Which is the ith binary string. Okay, so now that we have some natural correspondence between the integers, so these positive integers, and my Turing machines, I'm going to define a very strange language to you. Like, I mean really strange language to you. Something that it's going to make the last lecture just look kind of funny. And I'm saying that about something very important. I'm just saying that somebody very, very clever had to have come up with this language. So I'm going to define something called the diagonalization language. The moment you see this, this should kind of sit at you and say, that sounds kind of like last day, sort of. So I'm going to define the diagonalization language. So this is going to be the set of string WI such that WI is not in the language of the ith Turing machine. Let me write it more formally over there, but I just need you to think about this very carefully. So it's the set of strings WI such that WI is not in the language of the ith Turing machine. So while I go over to this board, I want you to think very carefully about what that means. So I'm going to write this more formally over on the other board, okay? So depending on how much time we have, I'll give you the idea of the proof. And then, depending on how far we get, I might do the rest of the proof next day. I was hoping we can get everything today, but we'll see. We might get lucky. Okay. So here's the language, the diagonalization language. So LD is the set of all binary strings such that WI, so remember this is the ith binary string, is not in the language of the ith Turing machine. Does anybody have any ideas what that means? It looks really strange. Like I'm saying that's kind of weird, right? It's very self-referential if you think about it, because remember, the ith Turing machine has a description that we've encoded previously as WI. So what does this mean? Can somebody tell me? Yes, yeah, that's effective. Yeah, that's effectively the idea. Let me write it in very plain language because, like I said, this is a very strange looking language. You might say, Dan, this looks really strange. Like, why would this even matter? I'm hoping in the next coming lectures, I'm going to convince you that these actually do really matter. In plain language, LD consists of all strings such that Turing machine M, whose description or code is W. So it'd be WI, but I'm just kind of keeping it simple. Does not accept W when W is the input. Weird, right? It's kind of strange. We've never really seen languages that do this. It's very self-referential. And when you have self-reference, you're going to run into very strange things in computing. That's really kind of going to be the big takeaway of this part of the course. Is things that self-reference themselves tend to have a lot of problems. There's a natural mirror for this in so-called set theory, like some of the stuff I talked about last day. But this is especially deep for us. So I'm going to make a table. So I'm going to draw the table out for you, and we'll come back to it next time, okay? But I'm just going to draw this table out for you. So consider the below, let me just make sure that's segmented off. Consider the below table. And I'm going to give you an idea for something to think about, because I'm going to show you the big idea when we get there. So I'm going to draw out a little table here. So I'm going to have, along the top, I'm going to have 1, 2, 3, 4, and so on. Along the rows, I'll have 1, 2, 3, 4. And I'm going to write some entries in here. I'll go 0, 1, 1, 0. I must stress that I haven't really checked the entries of these. It doesn't really matter for the purposes of this discussion, seeing as these could be any listings of Turing machines, just to be clear. I haven't even told you what the table means, just to be also clear. So here I have this table. Along this side are going to be each one of the jth binary strings. So when I say WJ, I'm talking about WI, but I'm talking about the columns. So this would be the first binary string, second binary string, third, fourth, and so on. I'm just giving J to indicate it's a column. For the rows, I'm going to have my Turing machines. So each one is going to be my Turing machine. Sorry, I'm going to call it, let's call it MI. So the rows are going to represent each one of my Turing machines. So this is where it's going to get a little weird. And it should give you weird hearkenings back to last day when I was around this exact time and I did something. Does anybody have any interesting, strange observations to make about this table? Think about what WJ is in a particular column and what the Turing machine is in a particular row. Does anybody have any ideas? Does anybody see anything that looks kind of like this? In fact, let me before I do that, suppose I told you that WI was in the language of machine MI. Where would that be located in this table? So look at the indices, I and I. So remember, these are going across the columns. The machines are down the rows. So what does it mean if both of them are equal? Diagonal, exactly. So the ones that we're going to be really interested in sit along the diagonal. Now this is, so if you look at each one of these entries, it actually tells you something, right? So each one of these tells you, well, if you read off the column, it tells you actually what is sitting there is basically something that looks like this, right? Perhaps we could do something to this diagonal akin to what I did last day with that set of all infinite binary strings. I'll let you think about that. But the other thing I want you to also notice is that each one of these rows represents each Turing machine. And if this is, suppose I told you that this consisted of all the Turing machines, every single one of them, because I know they're countable, right? I can list them like this in the rows. That's very important. So if I can do that, and I tell you that there's something funny I can do with that diagonal, perhaps I can describe to you strings that won't belong in any one Turing machine's set of strings. Because what each one of these rows actually tells us, this is the part I really want you to think about with this, is each one of these, you can think of this as the description of some string for which the wj gets accepted by machine mi. So you could think of this as a language, each one of these as the language, just like I said over here. So where a 1 appears, it means you know that that string will get accepted by that Turing machine. And so on, and so on, and so on. But remember, I'm talking about a binary string that's fed as part of, like, remember, these WJs represent descriptions of Turing machines as well. So it can be a little confusing. But I'll talk more about this next day. Just remember, these rows represent, you can think of these as what we call characteristic vectors that are going to each represent the language of each machine mi. So think about what you could do with this diagonal. I'll talk more about it next day, okay, everybody? So we didn't get quite to the result, but I'm telling you, this language right here is going to be a problem for our Turing machines. So I want to say thank you very much and have yourself a beautiful day. I'll see you later.